Hi, this is János, it's Real World Audio, and today we are talking about output transformers. Usually people associate output transformers with tube amplifiers only, but they are much more than that. Output transformers are devices, are transformers that do impedance matching from the power stage to the loudspeaker, and this can be used both for tube amplifiers and solid-state gear as well. And why is there a need for that? That's because there is an impedance mismatch between the output of an amplifier and the input of a loudspeaker. Practically always, the output of the amplifier is much higher than the input of the loudspeaker. What does that mean? We can translate that into an automobile, into a car allegory. It's like converting the RPM of your car into the rotation of the wheel. And the two need to be adjusted, and we have a gearbox for that. So the output transformer is like the gearbox for your audio. And that is because the output of your amplifier, it has higher voltage and lower current than what the loudspeaker would want to see. And we are converting voltage down to current with the output transformer. And for a tube amplifier, we need a much higher conversion ratio, so that's why there using an output transformer is mandatory. While, except for OTL amplifiers, but that's a special category. If you are not talking about that, just regular amplifier topologies, for a regular tube amplifier topology, you always must use an output transformer to match the output impedance, which is typically in the order of a kilo ohm to 10 kilo ohms. It can be even higher than that or lower than a kilo ohm, to the 8 ohm or 4 ohms or 16 ohms or 2 ohms that the loudspeaker wants to see. And what about solid-state amplifiers? Actually, even in the case of solid-state amplifiers, they would be the happiest of seeing something between 50 ohms to 100, 200 ohms. That's what the output of a transistor wants to see. That's where it's working optimally. And people are using the feedback loops, negative feedback, to make it possible that the transistor or your solid-state device can match the loudspeaker's low impedance. There are some companies like Macintosh who use output transformer to convert the high output impedance to exactly the impedance of your loudspeaker, and that's why such Macintosh output transformers, such amps, have like a 4 ohm tap, 8 ohm tap, 16 ohm tap, and whatever tap they have on that actual device, but they have specific taps for specific speakers, and you can impedance match your loudspeaker with those solid-state amplifiers that have the output transformer. On any other amplifier, the solid-state amplifier, there's no impedance matching because there's no transformer in it. And some people say that it's a really good thing because you are not facing the limitations of an output transformer, so you will have greater bandwidth and greater clarity. However, a big distinction has to be made, because when an output transformer becomes a limitation is when it was done on a budget, when it is done to a high level, then an output transformer actually elevates the level of your equipment, even if it's a solid state amplifier. But the raison d'etre of the solid state amplifiers is to make them cheap, which means cheaper to produce than tube amplifiers. That's why they don't have transformers. Macintosh was a company that prided itself by creating high-level, expensive amplifiers. That's why they had output transformers for their amplifiers, for their solid-state amplifiers, actually for some of them. And they sold at extremely high prices, like as if they were tube amplifiers, because of these transformers. They really were produced at an extremely high level, and that comes at an extreme cost as well. And most companies don't want to do that today, even though if they sell you an amplifier for $100,000, a solid-state amplifier, for that ridiculous price, they rather not design an output transformer for it, because that would cut into their profit margins. And of course, if I made an amplifier and my parts cost was $500 on it, and I'm selling it for $100,000, that's much better business than putting in a $10,000 worth output transformer and then making me $10,000 less profitable on that same model. So what makes an output transformer good quality, and what is a limited output transformer, what is a high quality output transformer? What makes them tick? So now what I'm showing to you, this is a very cheap, very basic output transformer. I was the one who added that copper band around it. It came without the band. It's a little bit tweaked, but it's the venerable Hammond 125 ESE. So this is what people used to use, I mean DIYers, who built their first tube amps 20 years ago. And I think throughout the ages, this has been the introductory level output transformer for tube amplifiers. And this unit is a 10 kilo ohm primary, but it has lots of secondaries, and you can use it as either a 10K, a 5K, or a 2.5K output transformer. So you have really a wide range of tubes that you can use it with. It is a 15 watt core. It has some weight, has some little heft to it, and it's, of course, it's a single-ended transformer. And single-ended output transformers have a lot of challenge, and that challenge compared to push-pull output transformers. And that challenge comes because they need to be gapped for a DC current. And when you need to gap for DC current, it means that the inductance is quite limited compared to a push-pull transformer. And if you want to attain high level of inductance for a single-ended transformer, you need to make it big. It has to be big. You need to have the core size for it. And you need to have enough turns to have high enough inductance to give it that low frequency bandwidth. Because for output transformers, the bandwidth on the low end, on the low frequency end, is defined by the inductance. And on the high frequency end, it is defined by the capacitance of the windings. So essentially, if you want to design or even if you want to purchase a good quality output transformer, then you must look at the inductance of the unit, which actually, if you look at the figure, like 10 henries per kilo ohm. So if you look for that, that's excellent, and that's what you want to look for just absolutely prodigious low frequency extension. So if you have like a 10 kilo ohm 10 Henry per kilo ohm inductance, which means, like, for example, if it's like a 3 kilo ohm primary output transformer, then if you have 30 Henries of inductance, then you will have low frequency in subterranean low frequency extension down to the limits, even below, down to the subsonics. You can use that for a system that can even handle subsonic, which means below 20 Hz frequencies with power, authority, presence, and flesh and guts. And when you drop to half of that, like 5 Henry per kilo ohm, that's still quite a lot, and even that is just the range of very expensive single-handed output transformers. And when you have these cheapo guys, this is not even 1 Henry per kilo ohm. This I don't recall exactly what's the inductance of this unit, but it's almost like a joke, like a laugh, and that's why people never consider it more seriously. But surprise, surprise, it still functions quite astonishingly, and it in that case, when you do not oversaturate the core, because the inductance is not an arbitrary unit, so it's not always like 10 Henries and then 10 Henries forever, but it's 10 Henries at the rated quiescent current. So there's a standby current, the quiescent current, that your output tube is constantly drawing, and that current is magnetizing. There's a constant magnetization of the majority of the magnetizable material of the core. So when you have a single-handed transformer, the majority of the lamination's magnetic potential is used up by your quiescent current. And the higher the quiescent current, the more it hijacks from the inductive capacity of the iron. And when you look at the specifications of the unit, then they specify, when you read that the unit has a certain Henries of inductance, then those certain Henries were measured at that milliamp current that they provided, which is the rated milliamps for that output transformer. Now, what that means is that in most cases, when you buy an output transformer and you run it at the rated milliamps, then you have those limited Henries of inductance that they published for that. And it's getting you nowhere to the zone of 5 Henry per kilo ohm, let alone the desirable or the God mode 10 Henry per kilo ohm level dream territory. And what you can do to get there for affordable iron is to stay at much lower quiescent current than the rated current. So in that case, that's why when I built my Darling amplifier, which had a quiescent current of 40 milliamps for the 2 Darling tubes, and I got this iron which was rated at 80 milliamps, so double. So what I'm using is that I'm using half the current, so it means that much less material is magnetized in the core, so I have tremendously more material that can be magnetized. So it means that in the low frequency range I have much lower extension to reproduce low frequencies, and I have much greater headroom for larger signals, for bigger dynamics to be passed through this output transformer. So essentially, when you buy a lower grade output transformer, just make sure that it's well oversized to compared to your application, and then it will behave as if it was a much higher inductance, much more capable unit. There will be one difference though between a cheap transformer used in that fashion versus an expensive transformer, is that the cheap transformers have high capacitance, high interwinding capacitance, which means that capacitance between the primary layers and the secondary layers, right? And then there's also multiple other forms of capacitances, but the primary secondary capacitance, that's usually the majority of the capacitances you see. But there's also capacitances within the primary and within the secondary coils as well. And by using more elaborate winding strategies, more elaborate interleaving strategies, then you can minimize the capacitance between the windings. And what that makes the difference is that for the cheap units, which have simple winding schemes, which allow the manufacturers to easily wind those coils, and because it can be easily wound, it can be mass manufactured more easily, that is, they can sell it cheaper. And these cheap units typically are like 3 to 2 interleaving, so like you have 3 primary coils and there are 2 secondary coils sandwiched in between. That's the absolute minimum that you can get by with a reasonably high quality output transformer. But that's the simplest. When you have a refined one, usually you have like 5 primaries and 4 secondaries interlaced. So you have 9 layers versus the 5 layers. And when you have like the really high level output transformers, like the Tangos, Hashimoto's, they have like split layers. So like within one layer of winding, within one unit, like one secondary winding, the winding is split into 2. So like physically 2 coils parallel next to each other, and even they play around with the direction of the coil and the winding to absolutely minimize the capacitance. But that makes it a much harder feat to design such a transformer and much harder to wind it. So instead of just having like an easy technician, like your beginner worker, being able to make like dozens of these units or maybe hundreds of these units a day, then when you have such a complex transformer, you need an experienced technician, and he can make like maybe like 5-6 units a day instead of the 100 units, because the winding scheme is so complex and it just takes so much more time and attention to create those transformers. And so when you have like limited high frequency range, that's because because of these design choices to make the transformer affordable. So when you have those people who are in favor of not using output transformers because they limit your sound, that they are not against the transformers, but truly in reality they are against cheap underspecified transformers, and they are absolutely right, because these transformers limit both your high frequency and your low frequency. And as I said, if you are DIY savvy, just get an oversized one, and then your low frequency won't be as limited as the specifications suggest, because they are specified for that specific high current, quiescent current, and if you are using a fraction of that, you will be in heaven. So for example, in my single-ended amp down here, which is like the 1.2 watts output amplifier, I'm using 30 watt rated transformers, and they are rated for 200 milliamp quiescent current, and I'm running them at less than 40 milliamps. And what that makes is that I'm just using the fraction, I'm magnetizing the fraction of that magnetic circuit, so I just have tremendous headroom, and I'm only using 1.2 watts instead of 30 watts. So by default, by wattage wise, I have tremendous, I have almost like a 30 times headroom, plus an additional 5 times headroom because I'm using 5 times less quiescent current. And what that results in is that even though I have a vast impedance mismatch with the transformer, in my output transformer to the speakers that I'm running them with, I'm still getting just astonishing low-end extension from these transformers. And because of the impedance mismatch, the bass is not as tight as if it would be where the impedance is perfectly matched. But regardless of that gross impedance mismatch, I'm still having even subsonic experiences which are just phenomenal. So I was just listening to, if I find Pink Floyd's Momentary Lapse of Reason, it was a beautiful experience. Even the cats OD'd out completely over the presence and the atmosphere of the of what the low-end energy created in the room, and the feeling that it created in my body. It was just phenomenal. And the secret for that was massively oversized output transformer. And yes, such experience, such prodigious bass can be had with single-ended amplifiers, because usually when you, I'm checking the time, okay, when you read about tube amplifiers, usually you see that for low-end extension you want push-pull amplifiers. They go much deeper and they're much more capable than single-ended amplifiers. My twist on that is to get your single-ended amps in the same ballpark, you need to massively oversize your output transformer. So hereby endeth the first lesson in output transformers. Thank you so much for chugging by. I hope it was useful, and thank you all who have been supporting me through Buy Me a Coffee. You are just amazing and help me tremendously. For example, in getting modern high quality transformers like one of these, and what that is I'm going to tell you later, and it's a surprise, and it's a surprise that was entirely made possible by you. So thank you, team. Bye bye.